Actually, there is a free electron theory in order to understand the different properties, electrical properties of materials. It was developed by Drude and Lawrence. And thereafter, this Drude and Lawrence model was modified by Sommerfeld, and it is known as the quantum mechanical or the quantum free electron theory. So, what is the basis of quantum free electron theory? That here you can represent the available energy levels of any of the electron by just drawing a line. So basically each of the energy level you can represent by energy lines for different quantum number, where each of the quantum number actually associated with the electron. And if you have an atom where you have one electron in the outer shell, so for one electron you have uh, energy levels for different quantum level. If you have two atoms in the outer shell, so you will have uh, two energy levels for each of the quantum number. For example, for n equals to 1, you will have two energy lines. For n equals to 2, again you will have two energy lines. And for n equal to 3, again you will have three energy lines. Let's consider we have atom 1 and atom 2, and both are having only one valence electron. That means it has one electron available their outer shell. So as it has only one electron. So let's say it will have one energy level for each quantum number. So we can have one levels for n equals to 1, that n actually representing the quantum number. For n equal to 2, you will get one more energy level. For n equal to 3, you'll get one more energy levels. So let's say, so this is the picture we are calling it a energy band. Similarly, let's say we have another atom, the atom 2, and it also have one valence electrons. It will have same one energy levels for each of the quantum number. Okay, but this is the picture of energy level for isolated atom. So now this when we are representing the energy levels for atom 1 and atom 2, so in this case we have considered that atom 1 and atom 2 are isolated to each other. But if you think about a solid where we have atoms, they are not isolated. That means inside the solid, the atoms are interact each other. There is an interaction between them. So let's see the example what happened when we have an interaction between the atoms. What happened to their energy levels? If we have a solid which made with two atoms, let's say atom 1 and atom 2. So what will happen? So basically, we will have overlapping of the energy levels of atom 1 and energy levels of the electron in atom 2. So for each quantum number, for n equals to 1, you will have two energy levels. For n equal to 2, again you will have two energy levels. N equal to 3, you will have two energy levels. So here you see we have a finite gap between the energy levels for different quantum number. Suppose you have an electron, that electron wants to sit in the available energy levels. How it will be sit? And that is actually governed by a rule that is called the Fermi-Dirac statistics and also the Pauli exclusion principle. For example, you can see here we have four energy levels available: E1, E2, and E3, E4. Let's see, we have seven electrons available. So how these seven electrons will be distributed among the four available energy states? That is actually determined or governed by the rule Fermi-Dirac statistics, that we will talk about details later on. How? So basically, it will be distributed like that. Only it will occupy a place only in the available energy states, not in the gap between these available energy states. So the energy levels where the electron can sit, that is we are calling it the allowed energy levels, and the gap where the where no energy levels are available, where no electron can sit, that we are calling the not allowed energy levels. So this is the simple picture of a solid where it is made with two atoms, and each atom has only one outer shell electron. Now, if you generalized this picture of a solid which made with two atoms for a solid made with five atoms. So what will be the picture of their energy levels? So all five atoms are interacting each other. That means so there will be overlapping of five energy levels for each quantum number n equals to 1, 2, 3. So for each quantum form, how many energy levels we will have? We will have five energy levels because all the five atoms are interacting each other. So this will be the picture of energy levels of a solid which is made with five atoms. So this is just a
Mhm.
broad outline of the energy pictures. Okay, now think about a real solid. You know that in real solid it is made with n number of atoms. And what is the value of n? It is the value of Avogadro number. So that means if you want to draw a energy level picture for a real solid which is made with n number of atoms, so that means for each quantum number you will have closely packed n number of, I mean capital N, the Avogadro number of energy levels, but this so number is quite high. I mean 6 into 10 to the power 23. So the interline gap is so small that instead of closely packed n number of lines, what we usually observe, we observe the energy bands for n number of energy levels here. That will form for same that will form energy bands for n equals, I mean the quantum number 1, again the energy bands for quantum number 2, energy band for quantum number 3. So this is the real picture of the energy levels for a real solid which is made with Avogadro number of atoms. And because of this huge number of uh, closely packed overlapping energy levels, you will not able to see individual atoms. So instead, you will see that energy bands. So that any electron can available any of the states available in the energy bands, but there is a finite gap between energy bands for n equals to 1 to n equals to 2. So this is the real picture from the band theory of solid. Okay, now we will see how electron can distributed in this concept or in this picture of energy bands, and then depending upon the energy band picture and the gap exists between this energy band actually determined what will be the uh, case of any material in which category it will falls. So again, I have redrawn it. You see, we have energy band for n equals to 1, 2, 3, 4, 5, 6. So you can move on in the upper layer. So basically, when we are increasing the quantum number equal to 1, so basically the energy levels is increased. The magnitude of this energy band is increased. So basically, it is in this the vertical axis scale. And now see, 1, 2, 3. The first four energy bands are shaded, and the next three is unshaded. What does it mean? So shaded means it is completely filled. If any of the energy band is completely filled with electron, that is the filled band. And let's say you have a material where first energy band is completely filled, second is also completely filled, third is also completely filled, and fourth is also completely filled. So then the highest completely filled energy bands we are calling it the valence band. The valence band is what? It is the highest field energy levels for any material. So that is the valence band. And the next empty band. So this is the valence band. The next empty band is this one. This is the conduction band. And the gap, the energy gap between the top of the valence band to the bottom of the conduction band is known as the band gap energy of the particular material or the band energy. And you can see that in this band gap region, there is no available energy levels. So no electron can occupy a space in this region. So in that sense, it is called the forbidden region because in this region no electron can sit. So in that sense, it is called the forbidden energy bands. And so conduction band is empty, and the rest of the energy levels of the energy bands in the higher energy levels all are empty or unfilled band. So in simple picture, at normal condition of T equals to 0 Kelvin, up to valence band, all the energy bands are completely filled with electron. And the next one is the conduction band. And conduction band and all the remaining energy bands in the higher energy levels are empty. So now apply this concept of energy level in order to distinguish any material into three categories, either in the metal, semiconductor, and insulator. So if you look into the energy picture of a metal, so in case of metal, what we usually observe that there is a partial overlapping between the valence band and the conduction band. So basically, there is no gap exists between the top of the valence band to the bottom of the conduction band. So as there is no gap exists, so band gap energy is zero. And another important point to be noted that as there is a partially overlapping, so you can have free electrons available in the conduction band even in the absence of any external electric field. So that's why uh, the metals give you very high value of conductivity even in the absence of any external electric field. So this is the reason. So now you can have an idea why metals have very high value of conductivity in the range of 10 to the power 6 to 10 to the power 15, because where we have overlapping, so the electron which was initially at the top of the valence band, now it can freely move inside the conduction band. So there is no forbidden gap. So now if you look into the energy band gap, if the gap is zero, so you can simply call it's the example of metal. Okay, and how much overlapping is there, that has to determine what will be the range of available free electrons. We have another scenario where you can see that the gap between the top of the valence band to the bottom of the conduction band is quite large. It is usually above 5 electron volt. Gap exists in case of this insulator, and it is quite large, above 5 electron volt. As this gap is quite large, so what is happened at normal conditions without any presence of external electric field or at T equals to 0 Kelvin, so all the electron will be remains in the valence band, so no electron can come to this conduction band. So valence band will be completely filled and the conduction band will be completely empty. So as there is no free electrons available in the conduction band, so the conductivity will be almost zero. That's why, so depending upon the gap, you can have a conductivity that will be almost zero. So that's why we have a scale of 10 to the power minus 18. Let's say you have a gap that is quite small, so then there will be a small chances of presence of few electrons in the conduction band. That will give you very finite conductivity. So example of this insulator is diamond, glass, wood. So in such materials, the large band gap exists, which is above 5 electron volt. So that's why no free electrons are in the conduction band. So conductivity is zero. And now we have a scenario where actually the valence band and the conduction band is separated, but the separation is not too small or not too high. So there is no overlapping, but also the gap is not very large. So that gap exists in the range of 0.2 electron volt to 4 electron volt in this short range. So as this gap is small, so at room temperature, when you have a temperature of 27 degrees Celsius, or you can say 300 degree Kelvin, so few of the electrons which can come to conduction band. So but only few of the electron can come to the conduction band. So you will have some conductivity, not exactly zero, but it will be very low value. So that is in the range of 10 to the power minus 6 to 10 to the power minus 10, 12. Okay, so you can see for one example is that if you look at the silicon, which is known as a element in a semiconductor, the band gap is 1.13 electron volt. For germanium, it is 0.67, zinc oxide 3.37. So in such material, the band gap between the valence semiconductors is quite small. So we can have a very low value of conductivity, not exactly zero or not in the range of 10 to the power minus 18, what we have seen in case of a insulator.